Okay, so the idea is to describe a little bit of what I call the entropy approach to these problems about fluctuations of large-scale interacting particle systems. So here in this workshop we have like two big communities of people. Some people coming from this renormalization quantum field theory, and another group that is coming from stochastic PDEs. So I'm kind of in a third group of probably one individual. So and what I do is much simpler stuff. I just look at this problem as with the classical Markov chain technique. Okay, so but since maybe you're not so expert in Markov chains as in renormalization group or stochastic PDEs, I'm going to go a little bit easier at the beginning. Okay, so well, the first thing is I want to write down a bunch of notations so later we understand what I'm talking about. So the first thing is, let me start with a Markov chain. Okay, so this guy here. So here time is continuous, and this guy is going to be a finite state Markov chain. Maybe this finite state, I going to call it omega at some point. So how do we describe this Markov chain? I'm going to describe it in terms of its generator, which is my favorite way to describe Markov chain, because later on that will allow you to do some calculus with it. Okay, so the generator of this Markov chain can be written as the following action over any function. Okay, so here we don't have to worry about anything because we are just finite state Markov chain, so everything is well defined. There are no renormalization constants or derivatives or two bounds to be worried about. And any generator of a finite state Markov chain can be written in this form. Okay? Where this Rxy is simply the rate of jump at which the chain jumps from the side X to the side Y. Okay, so this Markov chain, what does it do? Stay at some point, X, wait some exponential time, with instantaneous rate X of Y, and then jumps to Y. Okay? And so on and so forth, it keeps jumping around. And this is the generator. Okay? Well, one possible way to describe this dynamic. So this right here is the jump, right? Then I'm going to, in this set omega, let me consider a reference measure mu. So this is going to be it doesn't really matter which measure this guy here is. It's the only thing that I want to be sure of is that it has full support. Okay, that's what I call a reference measure. So for me, a reference measure is just a measure who has full support on the set omega. Okay. Next guy. So now that I have one reference measure, I'm going to take a sequence or maybe a path, a trajectory of reference measures. Okay, so for the moment these are just definitions. I hope they will start to make sense in a few minutes. What else do I need to define? I need to define now psi. Let me denote psi of t. It's just the Radon-Nikodym derivative of mu t with respect to the reference measure mu. Okay, this is why I need this guy to be positive everywhere, so I can do this quotient here. So this is the density. So this is the density of mu t with respect to mu bar. Then, okay, one more definition. Okay, if you don't see here, sorry, but I want to draw this blackboard in a few minutes. I really want what I'm going to write there to get to be there, okay? So this guy here is the density of the law of the chain xt with respect to the reference measure mu. Okay? Here I'm not specifying any initial condition for my chain yet, because some of the things I'm going to tell they hold for general initial condition, and some of them hold for some specific initial condition. Yes?
There's supposed to be probability measures? No.
Yeah. For me, measures are always probability measures. And it's a reference measure, which means that it's positive, so I can do this quotient here. Okay. So now, up to now are just definitions. Now I need a little bit less standard definition, which is the so-called Carré-Duchamp, which is just the second variation operator associated to the chain, which is, so it's the action of this operator gamma over a function f is this. Okay, so that's what is called the Carré-Duchamp associated to the chain xt. Just two more definitions until I write something meaningful. L star of t. Okay, so L star is the adjoint of L. Okay, but when you talk about an adjoint, you have to specify the reference measure. Okay, usually in Markov chains, when you talk about adjoints, you are implicitly assuming that the reference measure is the invariant measure. But as you may have noticed here, I haven't talked at all about the invariant measure of this chain, because I really want to assume that we don't know it. Okay? Which means that when I talk about adjoints, I have to tell you with respect to whom. So in this case, is the measure mu t. Okay, so that's why there is a subscript t here. So this guy here is the adjoint. Of L with respect to mu t. Okay, so now entering into business, I'm going to define h of t, which is going to be our main object of study today. So this guy here is the relative entropy of the law of the process xt with respect to the reference measure mu t. So this is going to be h of t. So this is what we call the relative entropy. So we have the following theorem, which is what I call the Gauss inequality. So Gauss inequality gives an estimate on the derivative of this guy. H prime of t is less or equal than minus the Carré-Duchamp of the square root of the density of t integrated with respect to the reference measure mu t plus something else, which can be written in the following way. L star t of 1, the function constant equals 1, minus dt log psi of t d mu. Okay? about this inequality, because this is the starting point of everything I'm going to tell you. Okay, so I think I define everything that appears in this inequality. So let's look at it in a more careful way. Okay, so if these measures mu t are just constant in time and the invariant measure of the original Markov chain, then this time derivative is 0 because it's constant in time, and then this adjoint here is actually the generator of a Markov chain, and therefore L star of 1 is equal to 0. So this disappears. Okay, and what we get is the very well known fact that the relative entropy of the law of a Markov chain with respect to the invariant measure is decreasing in time. Okay, this is a very well known fact, and this number here is sometimes called the Fisher information, the Dirichlet form, it has various names. So, a little bit lesser known fact is that if this is equal to 0, this fact here, so this thing here equal to 0 is exactly the Fokker-Planck equation. So it means that this thing here is equal to 0 if and only if the sequence mu t is the solution of the Fokker-Planck equation, meaning that it's the law of the chain starting from some other initial condition. So it means that, what does it mean that this is 0? It means that if you start two copies of the same Markov chain from two different positions, then the relative entropy between their laws is decreasing in time. So this is a fact which is a little less known than the fact that the relative entropy with respect to the invariant measure decreases in time, but it's also decreasing. So this factor here measures, in a sense, how far our reference measures mu t are from being the actual law of the Markov chain we are considering. Okay? So Gauss' idea to prove hydrodynamic limits, or in general to prove scaling limits of large Markov chains, is to guess a good mu t. Okay, if you have a good guessing of what mu t should be, how should mu t look like, then this term here is going to be small somehow. And then proving your favorite convergence theorem will be basically a task about proving that this term is actually small. Okay, so this is nice. And it's a very useful thing because it's a completely general inequality. So this is true for any Markov chain, for any Markov process. So in particular, it's true for diffusions, for SPDEs, for complicated things. Of course, then you have trouble defining the objects that are there, but it is still true. So it is actually a very sharp inequality because for diffusions, this inequality is actually an identity. Okay, so there is no less or equal in the case of diffusions, but it's unequal. Okay, so this is Gauss inequality. Okay, so everything actually I should have mentioned before, everything I'm going to say is, well, not everything, but most of the things I'm going to say, you can find in a paper that I just posted on Archive last week, which is called Non-Equilibrium. Fluctuations of interactive particle systems. And everything it's a joint work with my PhD student, Otávio, former PhD student, Otávio Menezes, which now is a postdoc in Lisbon. And so, in particular, you can find the proof of this inequality there. Okay? So now, let me just make the last comment on the inequality. This inequality, this idea of comparing the relative entropy between two solutions of the Fokker-Planck equation, or in general, maybe some partial differential equation, it's actually has been very productive in PDEs. Okay, that's the way which in PDEs, nice results about long-term behavior of solution of parabolic equations behave. Okay, so for example, if you take even a nonlinear heat equation, if you run it, let it run for a long time, it will start to look like the solution is going to look like a bell-shaped function. So it's going to converge to the fundamental solution of the heat equation. So now I'm going to tell you about another inequality that it looks similar to that one, and I like it because of that. And this is, it seems to be a new inequality. So, okay, so one more definition. So let's take a function v. So it depends on time and also on the position of our Markov chain. I want to estimate the exponential moment of this integral here. Okay, so this is what people sometimes call an additive functional. Of our original Markov chain, and in general, I like to call it an observable, okay? Because this is something we observe about our Markov chain, so it's something we observe, we integrate it in time, and usually we're interested in the behavior of this thing, of this integral for large d. Okay, so well, here it is just a finite Markov chain. So just from general theory, we know the Virgo theorem and also the central limit theorem for this guy here, maybe large deviations principle, nothing very fancy about it. But of course, at some point we are going to consider sequences of Markov chains, and we want some sort of effective bounds on expectations, variances, or maybe exponential moments of these random variables. And for that, it's good to have some sort of inequality. Okay, so we have the following inequality. So it's a bit strange looking inequality. But it's very interesting because it's related to the Gauss inequality. I described it above. Okay. So,
Are there some conditions on F?
huh?
Are there some conditions on F?
No.
When you take the carré de champ of square root of F.
Yes, so here I'm in the finite state setting, therefore everything is well defined because f is just is a function on a finite set. Okay, so in the concept of finite state Markov chains, everything is well defined. If you want to go to diffusions, you need to prove that these guys are actually well defined. Okay, so there you need some conditions, but people in stochastic differential equations have studied well this question, and they know under which conditions these things are okay. So the exponential moment of this additive functional can be bounded by some supremum, so this is a variational problem, and here f is a density, so the supremum here is over any density f. So in particular, there is no problem with the supremum because this set of densities here is compact because we are in finite state, so we don't have to worry about that part. But what is interesting here is that the structure of this variational formula is exactly the same as the structure of what we got in the Gauss inequality. Okay, so we have with a negative term the Fisher information, and then with a positive term we have the expectation of some function with respect to the density. Okay, and well, and of course we have the function v because the function v has to be there because it's what we are estimating, and there is an extra correction term which is exactly the same correction term that appears in Gauss inequality. What does it mean from a practical point of view? Okay, so the general situation is that you have a Markov chain with a large number of components, which can be very complicated. Then FT is basically not accessible. You can have some qualitative properties of the density FT. Okay, so maybe you have some bounds on moments or something like that, but you don't know much about FT because if you knew what FT would be like, then there will be no questions to answer, or maybe there are other questions to answer, but we have another set of tools to answer these questions about the large case limits or long time limits, etc. So when you arrive to that inequality, oh, there is an f that I missed. I always miss an f. Yeah, okay. So yeah. So in the paper, I miss this f, and here I miss the f here. Okay, so there it's kind of very nice to have the f there because it means that that integral that is written there is actually an expectation with respect to the process. An expectation with respect to the law of the process. So here you have the same term. Okay, so
But
up
this
there,
F is time dependent?
here no. Here you have the supremum over all densities. It's not time dependent. And there is some time dependence in the sense that for each time little t, this function f is a density with respect to mu t.
Yeah.
Okay, so there is that time dependence, but apart from that, no other time dependence. So how to, if one wants to take advantage of this Gauss inequality, what you need to know to do is to bound the rightmost term, the second integral, in terms of the first integral for any function f. Okay, so this is usually what you need to do. Well, if you want to do that, probably you also know how to do this one, because it's the same kind of problem, okay? So if you know how to bound the integral of more or less arbitrary, how arbitrary these functions are, it depends on what appears in the situations you want to apply this idea. But if you know how to bound the integral of more or less arbitrary functions, v or w, with respect to f du mu t, in terms of this guy which is here, then you have a tool that is going to be useful in one hand to get nice bounds on the entropy, then the relative entropy of your Markov chain with respect to the reference measure, and also for exponential moments of this kind of observable. So this sort of duality, I couldn't find in the literature this exact duality, but I mean, those related inequalities, they are everywhere. I mean, this is a very usual thing, and here usually this type of inequality. So how do we prove this inequality? Is just the Feynman-Kax formula. So the Feynman-Kax formula is something people have used a lot in various contexts. So similar inequalities to these ones abound on the literature, but this sort of duality between this inequality and that one, I found it very useful, and I don't know if it was pointed out before. Okay, so again, if you want the proof for this, you can find it on the article. So now we have to take a decision, and I'm going to ask you about it. This is very abstract, so this is complete. These two inequalities, they hold for general Markov chains, but if we don't see them in action, we don't really understand what is going on. So we need to make an example. Okay, so I have two examples in mind, so I'm going to ask you which one of the two you prefer. Okay, so one example on which you can use these ideas is what is called the exclusion process with the boundary conditions. Okay? And so you have particles on for example, on this line, and from here particles can enter and can get out with some probability. Okay, this is one set of example, and the other one is what I call mean field spin systems. And actually, I'm thinking about one particular example, which was recently studied by Benamou and Perez. So the dynamics is the following. Now it's a mean field model, so positions are not going to be relevant, but you have particles. And what you do is that at rate, at some continuous rate, let's say 1, you choose one side x and another side y, and what you do is that here you flip whatever you have here, so it goes to empty space to particle, or from particle to empty space. Maybe it's easier to put, instead of particles, put zeros as ones. 1, 0, 1, 0, 1, 0, 0. So what you do is the following. So to this digit here, you just add the digit here, modulo 2. Okay. So if you in this situation here, what is going to happen is that I'm going to switch this one to 0 to 1, or this one to 0, depends, because I'm going to add 1. So 0 plus 1 is 1, plus 1 is 0. So anyway, I'm going to flip. So but if here there is a 0, I don't do it. Okay, so this is a very simple example of a mean field in dynamics. So those are the two examples that I have in mind. This one is much simpler than this one, okay? But this one, it's more related to what I'm going to talk on Wednesday and Tuesday, so you have to decide.
Which one is similar?
This one is simpler.
Okay. But the other, you say one is simpler, but the other is related to.
So the other one is related to what I'm going to talk on Wednesday.
We don't know. Why you hesitate?
Because I don't know. Yeah, okay. Let's do the simpler one. Yeah, I think.
It's good to understand something simple.
Can you give a simpler proof of hydrodynamics than it is usually done by this?
I don't know if it's going to be simpler. I mean, it's simpler provided that you prove some difficult lemma, which is, which in my opinion is still simpler than the one block-to-block lemmas, but it's still difficult. But once you accept that, you can use it as a tool, and then it's very simple. I'm going to try to do that on Wednesday. So okay, so example. Infield spin system. So this is a work in progress with Freddy Hernandez. From Bogotá. Okay. So the state space is the space of a sequence of binary digits of length n. Okay, and so let me do some definitions. For eta here and x, let me call lambda n, the interval 1n. Then I'm going to define eta x. So eta subscript x is just the number that I obtain by flipping the digit at position x. Okay, so this is the original one plus delta x modulo t. Okay, so what I was explaining here. So you add to this one modulo 2, and the effect of that is just flipping. If you have maybe you can put more particles and do more complicated things. We can put here, I don't know, 0, 1, 2, and do more complicated things. But let's do something very simple. Okay, so my shape. So I'm going to take a function f. It's going to be smooth, and I'm going to define the generator of this chain in the following way. Okay, so there is some function f, some interaction function f, And the rate at which I'm going to flip the digit at position x is a function on the density of particles on my current configuration. Okay, so here I'm just adding y different from x because I don't want x to interact with itself. Okay, that's going to have an importance in 2 minutes. So this is my dynamics. So what my dynamics does is with some function which depends on the density of particles outside the site x, I flip the site x from 1 to 0 or from 0 to 1. Okay, so it's clearly mean field because there is no spacing structure. Or maybe there is if you think it's the structure is the structure of the complete graph. So now, okay, so let me write here and then put the black box up again. So this guy is invariant. Okay? So the uniform measure on this set here, which actually coincides with with the product of Bernoulli measures of parameter 1/2, is invariant for this system. Why? Because it's reversible. It's very easy to verify, satisfy the tile balance, and that's it. And that's why I'm adding sites outside X, because this is just a simple consequence of that the site X does not interact with itself. So if you don't put here y different from x, then you get the mean field Curie-Weiss model, and then the invariant measure is going to be different. Okay. So a very natural question in the theory of Markov chains is to describe its convergence to equilibrium. Okay, so that's what I want to explain now. Okay, so I'm not going to use this inequality in this example because it's not really needed, because actually the only function b for which I will need to do this estimate is the same that appeared there, so I don't really need it. So then Menezes consider the case f of u equals u. Okay, very simple. Okay. Although it may look very simple, it's very interesting because f of 0 is 0. Okay. What does it mean? It means that, so now we focus on this particular example. Okay. So then the L of f can be rewritten as the sum over x different from y, 1 over n, eta y, f eta x. So you choose two sides and random, x and y, and you flip x if there is a particle at y. So in particular, if there is 0 particle at the beginning, there is 0 particle forever. Okay? So this Bernoulli measure is not ergodic. But it's not ergodic just by a tiny bit, because actually if you start with 1 particle, you cannot go to 0 particle. Okay, so this invariant measure has 2 ergodic components. Everything 0 and the rest. Okay? So for any practical computation, if you consider the Bernoulli or the Bernoulli condition to have at least one particle, it doesn't really matter. So what Benamou and Perez prove? Okay. Okay. So I want to simplify as much as I can. So I'm going to. So let me call eta and t the chain generated by L, and let me assume that eta n of 0 has one particle. Okay, so our goal is to see how this chain converges to equilibrium, and it's very reasonable to think that one particle is the worst case scenario. Okay, because let's say you start with everything full, then it's going to start to go down, and you choose two sides at random, and in Y there is with a very big probability a particle, so you flip. You basically flip with probability close to 1. But if you start with just one particle, what happens is that most of the time at the beginning you choose two empty sides, and then you don't do anything. So you have to wait a long time until you choose the side with the only particle that is there, and then you flip another side. Now you have two particles, so you still have to wait a long time, but a little bit less, and so on. Okay. So this chain takes some time to get out of 0. And what they proved is the following thing. So
maybe I didn't understand the evolution as well as I thought.
okay,
The number of particles can change?
can change in time.
So I thought you were switching particles.
Okay, well it depends on what you call a particle. So
Yeah.
so there is zeros and ones. So
Yeah.
particles for me are the ones,
Yes.
and the zeros are empty sides.
Right.
So each time you choose, so you choose first x, the side that you want to switch, and then you choose y.
Yeah.
If there is a 1 at y, then you flip.
I got it.
So if there is not a 1 at y, you don't flip. Okay? Okay, so what did they prove? So they prove the following thing. Okay, so you can define Vt, and this Vt is going to be the distance to equilibrium. Okay, depends on n because the chain depends on n, and this is going to be so. Take your random. So take your Markov chain at time t and compare it with the measure mu bar. Okay, and look at the distance in in your favorite norm. Okay, so for probabilities the favorite norm is total variation because it has a very nice probabilistic interpretation, but maybe you can find more interesting Hellinger distance or Wasserstein 3 distance or whatever other distance you want. Okay, so you define this distance to equilibrium, and what they proved is what Benamou Perez proved is the following. They proved that
Sorry, eta n is the configuration or the law of the
is the law of the configuration.
Okay.
Okay, so I don't want to write. I don't want to be so picky with notation. So what they prove is the following. So they prove that what they call cutoff phenomenon. So instead of actually writing down what they prove, I'm going to draw a picture because it is much better. So here you have 3/2 log n. So they prove this result here, that if you take the graph of the distance in total variation, well, the maximum distance in total variation is 1. That's something you can verify. So it stays at 1 for a long time, and then goes very quick from 1 to 0, and then it stays close to 0 and goes to 0 as time goes by. And the transition point is 3/2 log n. This is what people call the mixing time. And the width at which this transition happens is of order 1. Okay? So it means that if you look at 3/2 log n minus 1000, then this distance is going to be close to 1. And if you look at 3/2 log n plus 2000, then this distance is going to be close to 0. So that's what we call the cutoff phenomenon. It's also what sometimes called abrupt convergence to equilibrium, because cutoff is used for so many things that maybe it's not a good idea to call something else cutoff. Okay, so this is what Benamou and Perez proved. And so they proved that the mix it's of order 3 log n, and the omega n is of order 1. So this omega n is called the window. Okay, so the window is the width at which this transition happens, and well, the window is of order 1. Okay, it's not 1, because it could be 100, 1000, and so what I want to explain you now is how to make a small improvement about this result, but more than an improvement, I saw it as a new proof. Okay, a new proof of this result. So how did they prove it? By the use coupling techniques. So Anna and Yuval are very good at coupling arguments, so they have a beautiful coupling proof of this theorem. But I want to do something different. Okay, I want to use this machinery of relative entropy to prove the same thing. Okay, so our theorem is actually the following. So there exists some function g, which looks like this. So it's again much better to just draw the function g. So it looks like this. So it goes to 1 at minus infinity, it goes to 0 plus infinity, doesn't touch 0 infinity, it's asymptotic, the convergence, and it's decreasing. It's strictly decreasing and continuous. Okay, so the existence function g such that you can actually write it down explicitly, but I don't want to do it. Such that what is the improvement with respect to this situation here is that actually we can describe how this curve here looks like. Okay, so in Benamou Perez they don't do that, and if you look at the arguments they wrote don't allow to do this, because in various places they make mistakes of order 1. Okay, so they make mistakes of order 1. It means that you miss this convergence here, because if you make a mistake of order 1, you miss the b here. Okay, so you have to do mistakes of order little o of 1 if you want to prove this kind of thing. But probably if you go through the proof and you improve every step on which they make mistakes of order 1, you can do it. Okay. So I don't want to claim that what we do is better than Benamu. It's just a different proof. Okay, so this is what we can do. And I want to explain you how to do this. Okay. So, what are the ideas? So the first observation that you can do is that so let me give a number to the density of particles, okay? So let me call pi pn, and this pi pn is going to appear on Wednesday again, but it's going to be local density of particles instead of global density of particles. So this is the density of particles. The number of particles divided by the number of stars. So if initially the number of particles converge to some density, so has some asymptotic density x0, which is strictly positive, then what do you have? You have a lot of large numbers. Okay, so this is very simple computation. You can do it in various ways. Usually what we do in my branch of business is that we write this guy here as a martingale plus an integral term. We check that the martingale converges to 0, and then the integral term gives you the integral version of this ODE. Okay? So you can prove this. Well,
Can I ask a question?
yes.
How do you scale your time here? Does it mean you still, in time 1, you still update n instance here, no?
So actually, I'm hitting the n scale of time here,
Okay.
because in the generator I write a sum over x instead of 1 over n sum over x.
Oh. Well, in your example, you had a 1 over n over. Are you in that notation or the one up there?
That's a very good question. Yes, I have here 1 over n, but here I have n squared terms.
Oh, yes, I see. Okay.
Okay, so there is an n hidden on the notation.
Okay.
Okay. So if you go to Benamu Perez, they have the n there. I think that they also do it in discrete time, but okay, so you have this convergence. This is very reasonable. Okay, so the density follows this OD. And since we are probabilists, each time we see a lot of large numbers, we are very tempted to prove the central limit theorem associated with it. Okay, so what is the central limit theorem? Well, you have to assume something a little bit stronger, because you also need to assume that the initial condition at the level of CLT converges. So if in addition, the square root of n pi 0n minus x0 converges to let's say psi 0, maybe you want to call it x0, so maybe you want to call it y0. Then you have a CLT. So you take out the log large numbers, you multiply by the square root of n, and then you converge to some process xt which satisfies an equation. Okay, so the equation that satisfies, so let me call this thing here minus v prime of phi. Okay, that's actually a very reasonable notation because each time you have an ODE on some right hand side, you're always very tempted to write it as minus v prime of something. Okay, this is just to facilitate my notation, but also because the theorem we are proving with Freddy, it's general, so it holds for any f smooth. So there are some difference in different regimes, but it's general. So here, so you have minus v prime, the usual thing. You have the linearization of your equation. And here you have actually and of course psi 0 is equal to y. Okay. So this is the CLT. So what these two things are telling us about our chain? Okay. It means that the number of particles is well approximated by a Gaussian random variable somehow. Okay. The mean of this Gaussian random variable is phi t, and the variance of that, well, it's actually the mean is n times phi t, and the variance of that random variable is going to be n times the variance of psi t. Psi t is a solution of a linear stochastic equation, and therefore it's a Gaussian random variable. Well, if you have patience, you can compute the variance. Okay, it's not very important. What is more important is that actually, if you got psi squared in this variance, so this guy here converges with t goes to infinity to 1/4. Okay, which is the variance of the density of particles with respect to the imagination. That's the only thing that we need to know. So we have somehow a candidate for a reference measure here. Okay, so we want something which is sort of Gaussian with the right mean and luckily the right variance. So you can do that. Yes.
Like that would only need order one time to equilibrate, right? Because the n only comes when you go when the log only comes when you start with very few particles, and here you always assume a Markov complete number of particles.
Ah, okay. So not really, because this 3/2 here is actually 1 plus 1/2.
Okay.
Meaning that the time your chain needs to get to x0 or epsilon is log n. And then the time your chain needs to follow through this ODE CLT thing is of order 1.
Okay.
And then at the end there is an extra 1/2 log n. Okay, so in other words, I mean, maybe this is something I can write here just as a quick comment. In general, if f of 0 is different from 0, then n is going to be 1 over 2 f of 1 half. Like that. And f of x, f of 0 equals 0, but f prime of 0 different from 0, then this 10x is going to be is going to be 1 over f prime of 0 plus 1 over 2 of f1 half. Okay, so there is a log n at the end of the life of your chain, which is this log n here, and that one is dictated by the behavior of the function f around 1/2, around the equilibrium, and there is another log n at the beginning, which is dictated by the behavior of the function f around 0. Okay. So now, what you postulate is that I'm going to take as a reference measure mu t. Bernoulli random variables of parameter phi t. Okay? So these are good, gives you the right mean. They don't give you the right variance. Okay, because the variance of that guy is phi t 1 minus phi t, and the variance of this guy here is sigma t squared, which well, I didn't compute, but I can tell you that it is not phi t 1 minus phi t. But from the point of view of entropy, relative entropy, we're not making a big mistake, okay? Because the relative entropy between two Gaussians is bounded. Okay, so maybe we're doing some mistake, and hopefully not too much. Also, for t large, this error is going to vanish. The error coming from the fact that I'm not taking here something with the right variance, because when t is large, then I'm actually taking the right variance. Okay, so well, you do this and then you postulate. Okay, let's see what happens. Okay, so you have to compute. And what is nice here about this relative entropy method is that once you fix an explicit reference measure, then this is also explicit. You can compute it. It's completely explicit. Okay? So you go and compute it. And so you discover that this is equal to, so this is a 1 minus 2 phi t, the sum over x difference on y, omega x, omega y, divided by n. Okay, plus, so this LOT means two things at the same time. So it means lower order terms, and also means lots of terms. So while this is a computation you have to do, and for some reason, when you do these spin systems or particle system, etc., these omega x functions pop up all the time. So it's a very good idea to give them. Okay. So this is omega t. So it's the center variable eta x, well corrected by this factor here, which is the variance. So I will send you the obvious question. Shouldn't be square root there? No. Well, you do the computations, and it's easier if you define it like that. Without the square root. Because if you do the square root of that, this will be variance 1, it will be nicer. So these functions, these omegas here are bad when the phi is close to 0, 1. So that's why maybe it's a good idea to start a little bit far from 0, 1. Okay, so I think that here we are done. Okay, so that the Gauss inequality plus this computation. Well, we are not done, but already tells you something meaningful. Okay, so this is inequality. So h prime is smaller than something negative plus the expectation of that guy there. What do we have here? So this is basically the center density, no, of particles. So, but okay, but some x different from y, it means that it is the square of the density. So I'm divided by n, which means that I'm in the right, in the right scale for the CLT. So this random variable here by the CLT should be like a Gaussian. And actually what you can prove is that it's a sub, so it's the square of a sub Gaussian random variable under Newton. Okay? Okay, so it's the square of the density, and the density is sub-Gaussian. Okay, what does it mean? Huh?
You were going to say that. What does sub-Gaussian mean?
Okay, so sub-Gaussian means that when you compute the exponential moments are bounded by e to a constant time theta squared. Okay, so it means that the moment generating function it's bounded by a parabola. Okay, that means sub-Gaussian, and what is important for us is that sub-Gaussian has small finite exponential moments for theta small, the square. Okay. Because it's like if it were stochastically dominated by a Gaussian, and the square of a Gaussian has finite exponential moment if the parameter is small enough. Okay.
So sub-Gaussian means that this is actually under, when you compute the exponential moment of the, it's smaller than the moment of exponential moment of ut.
So, well, maybe I just write it down because not everyone is super aware of these things. So let me call this guy here. Okay, what is it? Well, this guy is actually more or less like pi tn minus phi of t squared divided by n. No? And what I meant is that the expectation of e to the theta pi tn minus psi t, so divided by square root of n, is less or equal to e to some constant times theta squared. And here, well, it's not really the expectation. What I meant is the integral with respect to the reference measure mu. Okay, so this is what I meant. This is exactly what I meant. That this guy here has quadratic exponential moment. Okay? And if this is true, what happens is that the expectations of these functions here will, of increasing functions of this guy here are bounded by the expectations of Gaussian. Okay, this is what is important here. So. Yes. So I was just saying that then we are kind of done, a little bit at least, because so what happens now?
Sorry, this you don't. Okay, this is from the Bernoulli.
From the Bernoulli. That's the point. This is from the Bernoulli. Here, that's why I'm saying that is with respect to this measure mu t, because we are computing the expectation with respect to f, not with respect to mu t. Right? So this is the next step. Now you integrate, okay? So this is less or equal than, and now I use the entropy inequality, so I get the entropy. So the entropy of ft is what I call h of t, plus the log of the integral of the expectation of gamma times this guy there. Okay, so gamma over n phi t n psi t square mu. Okay? So now if you take gamma small enough, and here there is some explicit boundaries. It depends on phi. So phi has to be away from 0, 1. If it's away from 0, 1, then some gamma. Let's say that phi is between 1/4 and 3/4. Then this gamma here, if you take 1/20, you're okay. So what I meant is that it's a numerical constant. It's not something that depends on it. And then you're done, no? Because you have h prime smaller than something that you discard, plus a constant times h, plus another constant, multiplied by something that goes to 0 fast enough. This 1 minus 2 phi here goes to 0 exponentially fast, because it's a solution of the ODE. Okay, so this guy here, it goes like e to the minus, so it's lambda, where lambda is 2, in our example. Okay, because it's the v double prime at 1/2, okay, which I think is 2. No, it's 1. Okay. Yeah, it's 1. Anyway, the point is that it goes exponentially to 0. If it goes exponentially to 0, when you use Gromwald, what you prove is that ht is less or equal than h of t0 times some function f of t, where f of t goes to 0 as t goes to infinity. Okay? This is for any t, time t0. Okay? And here it's t0. Okay? Because this f of t0 is what? It's going to be the e to the integral between t0 and t of something which is integrable. So it's something that has nice terms go to 0. Okay, you can do the computation, not very difficult. It's just Gromwald theorem, or Gromwald's inequality. What does it say about our process?
So you really want f of t0?
Well, now I'm going to explain that. Okay, so this is true for any t0. So in particular, it's true for t equals 0, and for t equal big T. But the point is that this bound is independent on n. Okay, so if we prepare our initial condition in such a way that is very close to mu at time t0, let's say, then it's going to be close to mu t for any later time t. Close in the sense that the relative entropy is going to be finite, with an bounded by a constant that does not depend on it. Okay?
Sorry, can I just understand correctly what you were saying?
Huh?
So up there you calculated explicitly this derivative under the wrong measure, and now you kind of use this transformation to go to the right measure, but that produces this 1 over gamma h of t. But then that's a priori bad in the Gromwald because that would give you exponential growth, but it's not so bad because you have the big factor which goes to 0 exponentially.
Exactly.
And the other term you can ignore. So it's
No, the other term is also multiplied by the.
yeah, but it's not so bad. I mean, it's even better than that.
Yeah, it's even better that way.
Right, okay. Yeah.
So. summarizing, okay. So big if the law of time t0 is close to mu t0, then
This means close in relative entropy.
in relative entropy. Then eta n of t is close in relative entropy to mu t for any t bigger or equal than this. Okay? So this means this already proved the theorem if we start, let's say, at t0 with exactly this measure mu t0. Okay? Because so mu t, the distance in total variation between mu t and the invariant measure nu bar satisfies the theorem. Okay? So if you compare the distance between mu t and nu bar, you will get exactly this curve here. Well, not exactly this curve here because I have to handle the initial part of the dynamics, but you will get some convergence here like this. Yeah, that's you just compare mu t with equilibrium. Okay, so
But you have some bound then that bounds the entropy, bounds the total variation by the entropy then.
yeah, exactly.
What is that? Is that easy?
Yeah, Pinsker inequality.
Like 2 lines or something.
Yeah,
Pinsker.
yeah. It's
Pinscale?
So, and that's a very simple thing. So, there is a big if here, okay? So, let's say that I can prove this for any time t0 which is not very big. So, how will I proceed to conclude the theorem? So, first, I choose t0 very big, but independent of n, in such a way that this function ft here is small. Then I prepare my initial condition like this, or I prove that the system is very close to that, and then I run this entropy method, starting from there. Then I will have nice bounds, upper and lower bounds, on the distance to equilibrium of our yes.
In small, you can never get less than 1, right? I mean, small means 1.0001.
It
It doesn't mean 0.001.
No, it means 0 times 0.0001.
How do you do that?
There's a big if there still.
Oh, the f is still going
No, the f
is
the if is
1.001.
no, the f is the tail of something.
Uh-huh.
Okay, yeah. Okay, so yeah, the f is 1.0001, and then the h is epsilon,
Yeah, okay, yeah.
and then there's 1. Yeah. So now what you have to do is now to deal with this thing here. But we know that at time t0, this guy is close to this one, not in entropy, but because of this. We have this very simple theorem that tells us actually that the density of particles is very close to some Gaussian random variable. In which sense? In a very weak sense for our purposes, because this is just convergence in law. Okay? But that gives you something. Okay? So that thing there tells you that at least so it took me a while to realize the following very simple fact. If you have convergence in law of some sequence of random variables to a limiting random variable, then you can find a coupling between them such that they converge in probability. Well, after you rephrase it in the right way, it's obvious. But the point is that what I want to make is that this is also true if you take two different sequences, convergence to the same random variable. If you take two different sequences, convergence to the same random variable, then you can find a coupling between the two such that they are close, the difference converges to 0 in probability. So what does it mean? It means that so I can assume that pi nt0 is a distance little o of 1 over square root of n of binomial of parameter let me see. This is not true. What is true is this. Distance epsilon divided by square root of n of binomial of parameter n phi t 0 if t0 is large. Large but independent on n. Okay? So this argument that I just told you tells you that this guy is at distance little o of 1 over square root of n of some Gaussian random variable. This Gaussian random variable doesn't have the right variance. But if t0 is very large, it almost has the right variance. So it is at distance epsilon of this binomial here, which is very close to another Gaussian random variable with almost the same variance. So now, what I want to how I want to proceed, I want to say that if you start with a deterministic configuration, which is at distance epsilon square root of n of this binomial here, then after a very, very short amount of time, then you are close in total variation. Okay, so you have your system. You have here your product measure that you want to be close to. So if you start from a deterministic system, you're not close. But but if the density is the right one, you just wait a little bit, and things equilibrate, and now you're close in total variation.
So what are you using to get that? I mean, this entropy inequality, or?
Exactly. One more time.
Okay.
So now the secret is that since t is large, the density is away from 0, 1.
Yeah.
So if I try to use the entropy inequality again, I don't have the problem with the okay. Okay, sorry. No. So I'm starting with a deterministic configuration with, let's say, 1/2 of particles on one side and the other half empty. Okay, so density 1/2, but deterministic. That, of course, is very far from product measure, but it's very close for on the following product measure. The product measure with parameter 1 on the first half and parameter 0 on the second half. Then we use a combination. Instead of using uniform Bernoulli's measures, we use two different densities on each one of the sides, and we use again the entropy inequality. And now what is going to happen is that the factor phi t there explodes because it's close to 0 and 1. But also the expectations are very small because we started from something deterministic, so the expectation, I mean, eta x minus its expectation is very, very small. So you combine these two effects to prove that after a very small time, you create a very small entropy. So now you are close to product. And now you are able to close the So you use the entropy inequality twice. One, to guarantee that for large times, if you are close to equilibrium, you get close, you're close to the product measure. You're close to product measure forever. And to prove that if you start with something deterministic, after a very little time, t, you get something which is again close to a product measure. Now, inhomogeneous, but still product, so we still can be in business. Okay, so I think I will stop here because my time is over. So for Wednesday, I'm going to start to talk about conservative particle systems and hydrodynamics.
Any questions which we haven't already asked?
How explicit is your function G?
Explicit. So basically, so the idea, so then you assume that f of 0 is different from 0 forever. Okay? So because then it's easier to explain what the function is. Because what is going to happen is that it's going to be really, this function g is the distance between, it's written somewhere. No. No, it seems that it's not longer written now. Okay, so here you see that this density of particles is like a Gaussian with some variance which is close to 1/4 plus a mean. So this G basically is the distance between two Gaussians with the same variance but with different means, and they start to get close until they coincide. So this G you can write it explicitly in terms of that. In the case on which f is 0 at 0, you have to add the initial part. And the initial part is basically the coupon collector problem. No? Because from you start with one particle, to go to two particles, you have to wait times of order n, that will give you some exponential of some parameter, and then you keep going. And at the beginning, it's very difficult to erase a particle. Because to erase a particle, you have to choose two ones. And to add a particle, you have to choose a 0 and 1. So it's much easier. So at the beginning, it's just you can just couple with the coupon collector problem, and what you are going to obtain is that the time at which you arrive to this x0 is basically random with some law that you can express explicitly in terms of sums of exponentials. Okay, so you have to add to this function g the effect of these two guys. The sum of exponentials at the beginning, which will give you some Gamble distribution. No, it's not Gamble, maybe, I don't know. Some distribution. And the Gaussian part at the end. So, of course, if you want to write a formula, it's a mess. But you can describe it in words very explicit.
Any more? All right, thank you very much.